Hello, so let's try just a super simple force problem. Just an example of how to solve your general force problem. Here's a picture of what's going on. We've got a person of sorts pulling a mass along the ground. Now we're going to go ahead and say the ground is frictionless. The mass is 5 kilograms, and the force that's pulling is 10 newtons. And let's go ahead and find the acceleration. Okay, so in solving a problem like this where you're given forces or asked for a force, you're pretty much always going to take the following steps. First, you're going to want to do a free body diagram, which is a special kind of picture. There's an abbreviation for it. You're going to want to write Newton's second law, which is F equals ma, or the sum of all forces equals mass times acceleration. You're going to ask if the acceleration is 0, or in other words, the sum of the forces is 0, right? Because the sum of the forces is mass times acceleration. You're going to ask if that is so. Put an arrow there. And we are going to list out the sum of the forces. Etc. And then you solve. Okay, so those will make more sense as we follow them. So here I have a picture of what's going on. Maybe I drew that, or maybe the problem came with the picture. But it's not just a picture. We need a free body diagram. So let me make my free body diagram right here. It's a free body diagram of the mass, because the mass is the thing that's going to accelerate. So that's the acceleration I want to find. And all a free body diagram, besides a few things maybe like the ground, all it should have is the mass and the forces that are acting on it. So we've got one force, the force of the pull, and I guess maybe I'll just call it F. I'll call it F1 just for fun, of 10 newtons. We'll keep in mind we know that force. The other force acting on this thing, other forces would be gravity. The force of gravity, which, recall, equals mg. And m is that 5 kilograms. And then the other force is the so-called normal force. It points straight out of the ground, or straight out of the surface it's on. So if this was a problem with a ramp, the normal force would be pointing out of the ramp, straight out of the surface, whereas gravity would still be pointing down. Right? Just keep that in mind. Normal force doesn't always point up. It doesn't always point the opposite of gravity. It always points straight out of the surface. In fact, that's what normal means. When you have a surface and you have something coming straight out of it that's perpendicular in all directions, that's what normal is. Okay, so these are all the forces that are acting on our block. So that's my first bullet point there. We did the free body diagram. Next step is to write the sum of the forces equals mass times acceleration. Oh, well, I spoke too soon. One more thing my free body diagram needs is an axis. Let's call this the x direction and this the y direction. There we are. Okay, moving on. To write Newton's second law, I actually need to do it in both directions. The sum of the forces in the x direction equals mass times acceleration in the x direction, and the sum of the forces in the y direction equals mass times acceleration in the y direction. And believe it or not, that is it for this step. We wrote Newton's second law. Easy for us. It was probably a little trickier for Newton to come up with. So the next step is we ask, is the acceleration in either of these directions, ax, ay, are either of those 0? Because that would mean the entire sum of the forces in the corresponding direction is 0. So that's this next step. So let's see, well, in the x direction, let's think about it. It's being pulled. There's no friction. So I'm pretty sure it's going to accelerate in this direction, right? Alright, so I don't think that this is 0. Let's think about the y direction, though. Well, the y direction is our up and down, right? Well, it's certainly not going to accelerate into the ground, right? The ground is in the way. And it's even more certainly not going to just jump into the air, accelerate straight up into the air. No, it is going to stay is going to stay flat on this ground. It is moving in the x direction, accelerating in the x direction, but it's not even moving in the y direction. So no, this acceleration is 0, and so I can write that. Okay, so that's that step there. So our next step is this one here. What I mean is that we do literally mean the sum of the forces, right? So let's look in the x direction. The sum of the forces equals max, carry that down, and in this case it's equal to, well, F1, right? That's the only force in the x direction, it's just F1, so that's all I need to write there. Now in the y direction, well, we left off with a 0, so the sum of the forces in the y direction is 0, and that's equal to, okay, let's look in the y direction. We have n is pointing in the positive y direction, so n minus the force of gravity. See that? The force of gravity is pointing in the negative direction. Okay, and that's it for listing out the forces. And the last step is, well, it's a little vague, but it says solve. So once we've done this, well, we've done everything that the free body diagram can do for us. We drew the free body diagram, wrote Newton's second law, we determined which ones are 0, and we wrote out the forces. Now we just need to solve for what we want, which was the acceleration. Well, we said the AY, the acceleration in the y direction, is 0. So the acceleration in the x direction, that's the only acceleration that's going on. So if we can find that, that is the answer, right? So, well, we just need to divide over m, like so. And we get that AX is equal to F1 over m, which in this case would be 10 over 5. That's 10 newtons over 5 kilograms, which makes 2 meters per second squared. Okay, recall that a newton is not to be confused with my n of normal force right there. The unit 1 newton is 1 kilogram meter per second squared is the way to write it out. We get tired of saying that, so we call it a newton. So if you take a kilogram meter per second squared and divide out the kilograms, you're left with meters per second squared. So our answer is 2 meters per second squared. Now see, in this case, we didn't actually need to use the sum of the forces in the y direction to solve what we were looking for. Now in other problems, we will need the sum of the forces in the y direction, so you might as well just write them both. But in this case, the answer came right out of AX from the x direction. So there we have it, we solved, and those are our, what are they, 5? Those are your general 5 steps to solving one of these problems. Now, of course, they can make them more complicated, in which case we would need to add a few more steps here or there, but these are your basic steps that you'll definitely do for every force problem. You may have to do more, and we'll talk about that when it comes up.